This is the Satellite Foundational course for GOES-ART training on cyclogenesis, potential vorticity concepts. My name is Scott Lindstrom and I will be guiding you through this training. Other contributors to this training are listed. Learning objectives for this course are listed on this slide. Take some time to read them. The satellite information you will see includes water vapor channels, the air mass RGB, and the split water vapor brightness temperature difference field. This figure shows the climatological distribution of potential vorticity. Latitude is on the x-axis and height in kilometers is on the y-axis. Potential vorticity has a reservoir in the stratosphere and variability with latitude. The dynamic tropopause in red is the height of the 1.5 potential vorticity unit PVU surface. The dynamic tropopause generally exists lower in the atmosphere at higher latitudes, toward the poles, and at higher altitudes in the tropics. The transport of an upper tropospheric potential vorticity anomaly can affect lower-level synoptic flow and produce vertical motions via deformation of the isentropic surfaces. The dynamic tropopause, that is the 1.5 PVU surface, extends to much lower altitudes in the vicinity of the upper-level potential vorticity anomaly. This classic figure from the 1985 Hoskins et al. Paper shows that the upper-level potential vorticity anomaly induces a low-level potential vorticity anomaly, and then the two anomalies grow in concert during cyclogenesis when strong upper-level forcing as shown by the PV anomaly is driving cyclogenesis. There is often a good correspondence between an upper tropospheric potential vorticity anomaly and dry features seen on GOES water vapor imagery. In the example shown here, NAM40 model fields depicted a potential vorticity anomaly at the base of an upper-level low that was moving southeastward across northern Alaska. The dynamic tropopause was brought down to the 600 hectopascal pressure level in the vicinity of the potential vorticity anomaly near the northwest coast of Alaska, where dry air was also indicated in the water vapor imagery. This system produced several inches of snow over parts of the Brooks Range in northern Alaska on the first full day of summer in 2016. If you have access to ozone measurements from OMPS instruments on polar orbiters, for example, you will often see high concentrations of ozone when the height of the 1.5 PVU surface descends, because stratospheric air typically has high ozone concentrations. This example shows a total column ozone product from the Legacy GO sounder that is created with a 9.7 micrometer ozone band. It shows a very good correlation between a potential vorticity anomaly and high values of total column ozone. In the absence of a total column ozone product, high ozone features can often be identified qualitatively using an air mass RGB product. In this example of a rapidly intensifying hurricane force low over the North Pacific, the darker red to pink shades help to highlight an area of high ozone associated with the lowering tropopause beneath the potential vorticity anomaly. The GOES-R series Advanced Baseline Imager Instrument has 3 water vapor bands as noted in the labels, and these 3 water vapor bands help identify and track 3-dimensional aspects of potential vorticity anomaly features. In this example, note the pronounced drying, that is descent, that is occurring, especially notable in the 7.3 micrometer channel, as the tropical cyclone Leslie starts to undergo extratropical transition in response to the approaching potential vorticity anomaly from the northwest. This stepped animation, the complete animation is available at the link, shows GOES-16 mid-level 6.9 micrometer water vapor imagery during a period of warm seclusion intensification of the remnants of subtropical storm Leslie over the North Atlantic, beginning after 15 UTC on 26 September 2018. An upper-level potential vorticity anomaly approached from the west-northwest and was wrapped around. The dynamic tropopause, taken to be the pressure of the 1.5 potential vorticity unit surface, descended to the 660 hectopascal pressure level at 18 UTC on 26 September according to GFS model fields. This shows the GOES-16 air mass RGB at 6-hour intervals from 0Z on the 25th of September to 12Z on the 27th of September 2018. In addition, it has the GFS contours of pressure on the 1.5 PVU surface. The dynamic tropopause descended to 850 hectopascals at 6Z on the 27th of September, when the storm was producing hurricane force winds, and then down to 925 hectopascals at 12Z on the 27th, when the storm was producing storm force winds. The air mass RGB images highlighted the signature of the potential vorticity anomaly in shades of red as it approached from the northwest and then wrapped around the southern and western portions of the storm circulation. In the inset, note a strong signal in green that exists in the split water vapor difference, that's 6.19 minus 7.3 micrometers, shown for the same times as the air mass RGB. The split water vapor difference is the red component of the air mass RGB. Here is a summary of the key points discussed in this training. GOES-R satellite imagery can help diagnose where potential vorticity intrusions into the troposphere are occurring. Those are regions where strong cyclogenesis might occur. You can find additional information pertaining to water vapor imagery, the air mass RGB and split water vapor difference products, and potential vorticity anomaly cases at the links listed here. This concludes the Satellite Foundational course for GOES-R on cyclogenesis, potential vorticity concepts. Thanks for listening.